Welcome back, everybody, for another deep dive. This time, we're going to be tackling something,
Should be mind-bending.
yeah, pretty mind-bending.
Yeah.
Chaos theory, the butterfly effect, and how these concepts might even connect to, the idea of free will.
Oh, yeah.
So buckle up. We're about to go on a wild ride through the realms of math, physics, and maybe even a bit of philosophy.
Yeah, what's really intriguing is how these ideas, while grounded in science, can really challenge our fundamental assumptions about how the universe works and the nature of our own choices.
Absolutely. And our source material today is a fascinating YouTube video
Oh, cool.
from the Tem Ciencia channel titled Chaos, Efeito Borboleta y a Matemática do Livre Arbitrio. And it explores some really thought-provoking questions.
Awesome.
Have you ever heard that saying, a butterfly flapping its wings in Brazil can cause a tornado in Texas?
Yeah, that's the classic example of the butterfly effect.
Right.
It captures the essence of chaos theory, the idea that small changes can have huge, unpredictable consequences. Exactly, and this video dives deep into how that concept might shake up our understanding of cause and effect, even potentially impacting the debate about whether we truly have free will.
To really grasp that connection, I think we need to rewind a bit.
Okay.
Let's go back to a time when scientists envisioned the universe as a giant, predictable clockwork mechanism.
Oh, like those elaborate clocks with all the gears and pendulums ticking away in perfect synchronicity?
Exactly. Think of Newton's laws of motion. Every action having an equal and opposite reaction.
Right.
It led to a view of the universe where everything unfolded according to strict deterministic rules.
So if we knew the position and velocity of every single atom in the universe at this very moment, we could theoretically predict everything that would ever happen.
That was the prevailing idea,
Okay.
and it was captured beautifully by a thought experiment from the early 19th century by Pierre-Simon Laplace. He imagined a hypothetical being now known as Laplace's demon.
A demon?
Yeah.
That sounds ominous. What did this demon do?
Laplace's demon possessed infinite knowledge and computational power. It knew the precise location and momentum of every single particle in the universe, and using that information and the laws of physics, it could perfectly predict the future and reconstruct the past.
So in this demon's view, the universe is like a movie playing out on a predetermined reel. Everything, including our choices, is set in stone.
That's the unsettling implication of Laplace's demon. If everything is preordained, does free will even exist?
Yeah.
It's a question that has haunted philosophers and scientists for centuries.
That's a pretty heavy concept to start with. But our deep dive doesn't end there, does it? Tell me we're about to challenge this all-knowing demon's grip on the universe.
We are, and that's where chaos theory comes in. This field of study revolutionized our understanding of how systems, even those governed by simple rules, can behave in wildly unpredictable ways. And it all started with a meteorologist named Edward Lorenz
Okay.
back in the 1960s.
So Lorenz was trying to predict the weather, kind of like a mini Laplace's demon, right?
Yes, in a way, Lorenz was using computer simulations to model weather patterns. He believed that if he had enough data and the right equations, he could forecast the future of the atmosphere.
That makes sense, but something must have gone wrong, or we wouldn't be talking about chaos theory, right?
You're absolutely right. One day, Lorenz decided to rerun a previous simulation, but he rounded off a few decimal places in the initial data. He expected the results to be almost identical, just a slight variation.
A tiny change in the data shouldn't have such a drastic impact on the outcome, right?
That's what Lorenz thought too. But he was in for a big surprise. When he compared the two simulations, he was astonished to find that even this minuscule difference in the starting conditions led to completely different weather predictions.
Wait, so changing a few decimal points in the initial data created a completely different forecast? That's incredible.
It is, and this is where that famous butterfly effect comes in.
Okay.
Lorenz realized that the weather is incredibly sensitive to initial conditions. Even something as small as a butterfly flapping its wings could, over time, lead to significant changes in weather patterns.
Okay, that raises a lot of questions.
Sure.
If the weather is this sensitive to small changes, does that mean our weather forecasts are doomed to fail? And how does a tiny butterfly cause a giant storm?
Those are great questions. And they get right to the heart of what makes chaos theory so fascinating and challenging.
So it's not like the butterfly is literally like creating the storm with a single flap of its wings, right?
Exactly. It's more about how tiny changes can propagate and amplify through a complex system.
Okay.
Imagine a chain reaction where one small event triggers another, and and eventually leading to a much larger outcome.
Okay, I see. So chaos isn't just randomness.
Right.
It's about this interconnectedness and the potential for unexpected consequences.
Exactly.
But how does this give us back free will?
Remember Laplace's demon.
Yeah.
It needed perfect knowledge of the initial state of the universe to predict the future with absolute certainty.
And chaos introduces this element of unpredictability.
Right.
So even the tiniest errors in the demon's knowledge could throw off its predictions.
Precisely. If even the slightest uncertainty can make the future unpredictable, then perhaps our actions aren't simply predetermined consequences of the past. Maybe there's room for genuine choice.
So maybe chaos provides a loophole for free will to exist. It's not that the laws of physics don't apply, but rather that the inherent unpredictability of complex systems makes it impossible to determine everything in advance.
That's one way to look at it. It's like the universe is playing a game with loaded dice. We can't know for sure how they'll land, even if we understand the physics of rolling.
I like that analogy. So chaos adds this element of surprise to the game of existence. But can we get a bit more concrete here? What are some real-world examples of how this actually plays out? I mean, besides the weather, of course.
Absolutely. Chaotic systems are everywhere.
Yeah.
Think about a double pendulum, for instance. It's basically two pendulums connected together.
Okay, I'm picturing that. So it swings in a more complex way than a regular pendulum.
Much more complex. And what's fascinating is that even a tiny change in the initial position of a double pendulum can lead to drastically different, unpredictable patterns of motion.
So you can't easily predict where a double pendulum will end up.
Right.
Unlike a regular pendulum, which swings back and forth in a predictable arc.
Exactly.
Yeah.
Its long-term behavior is highly sensitive to its starting conditions, just like the weather.
Okay, I'm starting to see how this chaos thing works. Small changes, big effects, everything is interconnected.
Right.
But it's still a bit abstract. Are there other examples, maybe something a bit easier to visualize?
Have you ever heard of the Mandelbrot set?
Yes. It's one of those mesmerizing fractal images, right?
Yeah.
They're infinitely complex, but I remember hearing they arise from fairly simple mathematical rules.
You're exactly right. The Mandelbrot set is a perfect visual representation of how minute changes in a number, when plugged into a simple equation over and over again, can lead to a dramatically different outcome.
Wait, so you're telling me that entire universe of complexity comes from a simple formula?
It does. And here's what's mind-blowing about the Mandelbrot set. You can zoom in on it forever, and you'll keep finding new details, new patterns. It's a never-ending journey into a world of infinite detail.
Okay, so we've got weather patterns, swinging pendulums, and these hypnotic fractal shapes. What's the common thread here? What makes them all examples of chaos?
It all comes down to that sensitivity to initial conditions. Even the tiniest discrepancies can amplify over time, leading to vastly different results. That's the essence of chaos.
So in a way, chaos is about embracing the unexpected. It's acknowledging that we can't always control and predict everything, which is a bit unsettling, but also kind of liberating, don't you think?
I agree. And it's not just about unpredictability. It's about the incredible beauty and complexity that can emerge from seemingly simple rules.
I love that embracing the unexpected beauty of chaos. It's a bit like life itself, isn't it? Full of twists and turns you could never have predicted.
It is.
Yeah.
And perhaps this inherent unpredictability is what gives us the freedom to make choices that genuinely matter, to shape our own destinies.
That's a profound thought. So we've journeyed from Laplace's demon and its deterministic universe to chaos theory and the possibility that our choices actually matter. Quite a leap.
Indeed. But there's another crucial insight from the Temsientia video that we should unpack. It delves into the distinction between determinism and predictability.
Oh, that sounds interesting. Lay it on me. I'm ready for another mind-bending concept.
Remember, determinism is about how the universe operates according to fixed laws.
Right.
Predictability is about our ability to accurately forecast what will happen based on those laws and our knowledge of the present.
Right, so even if the universe is deterministic, that doesn't mean we can perfectly predict everything that will happen.
Exactly. The video uses a really clever analogy to illustrate this point.
Okay.
It compares our understanding of the universe to knowing the rules of a game. Even if we know all the rules, we can't always predict the outcome.
I like where this is going. So it's like we might know the laws of physics, but that doesn't mean we can perfectly predict how they'll play out in every single situation.
Precisely. There are just too many variables, too many subtle influences that can shift the course of events. It's like a game of chess.
Okay.
We know the rules, but there are so many possible moves, so many strategies, that it's impossible to foresee every outcome with absolute certainty.
That makes perfect sense. But how does this connect back to chaos and the question of free will?
Well, the video argues that chaos introduces a fundamental level of unpredictability into the universe. Even if everything follows deterministic laws at the most fundamental level, the sheer complexity of systems, like the weather, the human brain, or the stock market, makes them inherently impossible to predict with perfect accuracy.
So even if we had a supercomputer that could process all the data in the universe, it still couldn't tell us exactly what's going to happen next. There would always be some element of surprise.
Exactly, and that's where free will might come in. If our choices and actions are not simply the predetermined results of a cosmic script, then perhaps we genuinely have the power to shape our own destinies.
Wow, that's a pretty empowering thought. So even if the universe is playing by a set of rules, those rules might be so complex, so sensitive to tiny changes, that they actually create space for genuine freedom of choice. It's like the universe is designed to surprise us.
Precisely. And that leads us back to that fascinating visual representation of chaos that we talked about earlier, the Mandelbrot set.
Oh, right, that infinitely complex fractal shape.
Yeah.
What does that have to do with free will?
Well, the Mandelbrot set exemplifies how simple rules can give rise to incredible complexity. It emphasizes this crucial point. Even if we know the rules, we can't always predict the outcomes.
I'm intrigued. Can you remind me how this Mandelbrot thing works? I'm a bit fuzzy on the details.
Of course.
Yeah.
Imagine you have a simple mathematical formula. You start with a number, plug it into the formula, get a new number, and then plug that new number back into the formula, and so on.
Okay.
You repeat this process over and over again.
This sounds simple enough. It's like a mathematical feedback loop.
Exactly. But here's this catch of this. Some numbers, when you keep plugging them back into the formula, will eventually explode to infinity.
So they just keep getting bigger and bigger without any limit.
Yes. But other numbers, even if they're very close to the ones that explode, will stay within a certain range. They'll bounce around, but never escape to infinity.
So tiny differences in the starting number can lead to completely different outcomes, either staying bounded or exploding to infinity. That sounds familiar. It's like those tiny changes in Lorenz's weather model that led to wildly different predictions.
You've got it. It's chaos in action playing out in the world of mathematics. Now, the Mandelbrot set is a visual representation of all the numbers that don't explode to infinity when you apply this iterative process.
Okay, but how do you actually create an image from that? How do you turn numbers into those mesmerizing fractal shapes?
Imagine each point on a computer screen representing a different number.
Mhm.
If the number, when plugged into the formula, stays bounded, we color that point black. If it explodes to infinity, we color it a different color depending on how quickly it escapes.
And that's how you get those incredibly intricate patterns and shapes. It's amazing that such simple rules can generate such mind-boggling complexity.
It is. The Mandelbrot set is a stunning visualization of how simple rules can lead to unimaginable complexity. It also demonstrates how tiny variations in starting conditions can create wildly different results.
So it's like a visual metaphor for chaos theory itself. You can zoom in on the Mandelbrot set forever, finding new patterns and intricacies. Just like in a chaotic system, there are always new surprises lurking beneath the surface.
You've got it. And that's why the Mandelbrot set is so relevant to our discussion of free will. If even something as seemingly simple as a mathematical formula can generate such unpredictable complexity, imagine the possibilities within the vastly more intricate systems that make up our universe in our own minds.
Okay, now I'm seeing the connection. It's like the Mandelbrot set is a reminder that even if the universe operates according to deterministic laws, those laws might be so complex, so sensitive to subtle variations, that they actually create space for true freedom of choice.
Precisely. And that's a pretty empowering thought.
It is. But I have to admit, my brain is starting to feel a bit overloaded. Can we try to sum up what we've learned so far about chaos and how it relates to free will?
Absolutely. We've covered a lot of ground, from deterministic universes to unpredictable weather patterns to mind-bending fractals. It's a lot to take in.
Yeah, I feel like we've really been on this incredible journey exploring like everything from, that deterministic vision of Laplace's demon to this surprising world of chaos and the butterfly effect.
It is a lot, isn't it?
We even zoomed in on the Mandelbrot set.
Yeah.
And witnessed how simple rules can give rise to unimaginable complexity.
Absolutely.
It's a lot of process.
It is.
So before we wrap things up, I guess,
Yeah.
let's try to distill like the essence of this deep dive.
Okay.
What are the key takeaways we want our listener to walk away with?
I think the most important takeaway is the realization that determinism and predictability are not the same thing.
Okay.
Just because the universe operates according to fixed laws like the laws of physics doesn't mean we can perfectly predict the future.
Right. Chaos throws a wrench into the works. Even the tiniest uncertainties can amplify over time, making long-term predictions impossible. It's like trying to predict where a leaf will land in a hurricane.
Exactly. And this inherent unpredictability isn't a flaw in the system. It's a fundamental feature of complex systems.
Right.
It's what makes them so dynamic, so full of potential for both surprise and wonder.
And perhaps it's what saves free will from the clutches of Laplace's demon.
Right.
If the future isn't completely predetermined, then maybe our choices and actions really do matter.
That's a thought-provoking possibility. Chaos theory doesn't prove the existence of free will, but it certainly opens the door to that possibility.
Right.
It suggests that even within a universe governed by laws, there might be space for genuine agency for us to genuinely shape the course of events.
It's both humbling and empowering to think that our actions, even the seemingly small ones, might have ripple effects far beyond what we can imagine.
Absolutely. It highlights the importance of understanding the rules of the game, the laws of physics, the principles of economics, the patterns of human behavior, while also acknowledging the inherent uncertainty and complexity that shape our world.
So embracing chaos isn't about giving up on understanding the world.
No.
It's about recognizing its limits, accepting the unexpected, and appreciating the beauty of the unknown.
I couldn't have said it better myself.
So one final thought
Yeah.
for our listener to ponder. If our universe is truly chaotic,
Right.
what does that mean for our understanding of cause and effect? Does it suggest that the future isn't a fixed destination,
Right.
but rather a vast landscape of possibilities shaped by the choices we make every single day?
That's a fantastic question. And I encourage our listeners to keep exploring these ideas, to delve deeper into the fascinating world of chaos theory, and to see how it might change their perspective on everything from everyday decisions to the grand mysteries of the universe.
Absolutely. Keep those minds open, embrace the beauty of the unexpected, and keep exploring this amazing chaotic universe we call home. Thanks for joining us on this deep dive.